So your next lesson is going to be on interconverting between real numbers in rectangular form and in polar form, and seeing the connections between those. So I'm going to just kind of do a little table here where I have a real number that's going to be symbolized with the R, and this is a real number, -16. What you are kind of hopefully seeing this is that this is actually a position on a graph, on a chart of real numbers and imaginary numbers, and this would be left 16. So given that, the interpretation of this is that that's at an ordered pair -16, 0, or what we're going to say is -16 plus 0i. I just taught this yesterday to a different class in kind of a more simplistic level, and there was a lot of struggle on why -16, 0 is the ordered pair. But yeah, so the rectangular form is kind of what we're going for, and this is the rectangular form now of a complex number, and that complex number in a plus bi is a number that we say is in R2. This is a notation you will not find in your books, but you will find it in college, that it's a two-dimensional real number. So we call this R2. There is such a thing as R3 and Rn. Okay, polar form. Polar form is completely different. This is the Re to the theta I. And as Re to the theta I has it, we now have a radius of 16, a base value of e to the pi I, because pi is the angle here. If I track that, I get an angle of pi. So that's in essence what's happening here, and that's where we have a radius and an angle, and we're just going to be trying to do the interconversion. So let me try with the real number 8. 8 would be 8 plus 0i, because it'd be the ordered pair 8, 0, and that would be a radius of 8, e to the 0i, since that would be the best and most simplistic angle to use. You can also say 8e to the 2 pi I, or if you want to get clever on me, 8e to the tau I, but the best and simplest one is actually 8e to the 0i, which, yes, is just 8, since e to the 0i is 1. So that's, whether we keep the zeros or not, we're just understanding the differences between the forms. And then you have numbers that actually can't really go at all on the real chart. So they're not real, they're pure imaginary. If I have I'm going to kind of go up here, real, or let's put a little slash here, imaginary, which gets the notation of little I. So I'm just going to put a -2i here. Well, the rectangular form would be 0 minus 2i, and the complex, or the polar form, would be 2e to the, well, if it's -2i, that is down on the axis, so that's 3 pi over 2i. And finally, let's just kind of convert two in different directions. Let's go 7 minus 3i. And now I kind of have to think about where this is. This is going to be a little tricky. I'm just going to do one of these because if I have a radius, when it's just kind of radius would be equal to square root of 3 squared plus 7 squared. So that is 49 plus 9, or 58. So this is root 58, which doesn't simplify. The theta would be equal to, well, on this, I would really want to track where that is. It's right 7 down 3. So that's right here. And since arctangent outputs angles in quadrant 4, I would be okay with this. This is the arctangent of negative 3/7, because y is 3 and x is 7. So my polar form would actually be root 58 e to the arctangent of -3/7 I. Well, let's keep going with a few others. I just kind of want to show this. What happens if it's in quadrant 2 or 3? Let's do -1 plus 2i. So, new example. -1 plus 2i would have a radius of the square root of 1 squared plus 2 squared, which is equal to √5. And the theta, since this is popping up into quadrant 2, and arctangent, well, arctangent only outputs in quadrant 4, I know that theta would have to be equal to the arctangent of -2, but since the arctangent of -2 is a negative number, I'd have to add pi to that to make sure that that pops up into quadrant 2 instead of being an angle in quadrant 4. So my polar form would be √5e to the pi plus arctangent of -2 times I. Okay, continuing on to some other types of problems. We started to allude yesterday at how squaring and other operations are far easier in polar form than they are in rectangular form. For instance, if I gave you this and I asked you to square that and to give me the polar form of the square, this means we'd want to convert that to polar form first. So let's do this. If I have √2 plus √3i squared, I know that the radius is equal to the square root of 2 plus 3, which is also now the square root of 5. And the angle is just a basic arctangent. This would be the arctangent of √3/2. If I put √3 over √2, you can just express it as a single radical. That's okay. And so I would end up with √5 arctangent, or sorry, e to the arctangent of √3/2 I, and I'm squaring that. So my final would just look like 5e to the 2 arctangent of √3/2 I. So angle is twice whatever arctangent of √3/2 is. And that would actually be a final polar form of this. This also allows you to do exponents that are very, very large. So I would never want to do √5 plus I to the 100, even if I was really great with my binomial expansion. That would be a pain. And as you know, with the i's, it starts to cycle back on itself. So what's really happening? Well, if I convert this into a radius, which would be the square root of √5 squared plus 1 squared, so radius would be √6, and my theta is equal to the arctangent of 1 over √5, then this really converts to √6e to the arctangent of 1 over √5 I to the 100, which is the same thing. √6 to the 100 is 6 to the 1/2 to the 100, e to the 100 times the arctangent of 1 over √5 I. So 6 to the 100, or 6 to the 1/2 to 100 is just 6 to the 50th, e to the 100 arctangent of 1 over √5 I. And that would be an exact answer. You don't need to really do anything with that. So those are some extreme examples of what you're doing, converting into a polar form and then performing the operation that is made easier by converting it into polar form. One thing that, since I've got time, I kind of want to show. Your worksheet isn't the world's most difficult one, so that's okay. Well, I'll show one more problem type you have on it. So let me just kind of check my number type, and then I'll do the fun stuff. Let's say that I have 4 times the cosine of 10 degrees plus I times the sine of 10 degrees. And I want to raise that to the 4th power. I put this down because this form of polar coordinate, or polar complex number, is a form that you see in your textbook and in another textbook. So you see that a lot. the reason I told you I don't like that form. I think it's unnecessary for e to the 10 degrees, which I'm keeping in degrees because we haven't done degrees in a while. 10 degrees I, raise that to the 4th power, and what I'm really getting is 4 to the 4th, which is 2 to the 2 squared to the 4th, which is 2 to the 8th, and 2 to the 8th is 256. E to the, well, I can multiply 40 degrees I. Now, if I really want to express that as a better complex number, I probably should convert 40 degrees into radians. So pi over 180, and that would give me 2 pi over 9. So this is 256 e to the 2 pi over 9 I. And that's the correct form. Okay, let's go back to something fun. I want to show you 2 little fun things that I kind of was hoping to be able to do today. I was not going to be able to do if it was a 40, and then when we got the call on the virtual learning day, I can do this. So let's do 2 operations that you could not do otherwise. Let's take the natural log of -7. This is crazy. You can't do natural logs of negative numbers because a natural log is a number that when I take e and raise it to a power, I get -7. And you can't take a positive base, raise it to a number, and get a negative number. But you can do this in complex numbers, and it's not terribly hard once you know how to convert -7 into its polar form. -7 is left 7 units, up 0. That's a radius of 7, e, raised to the angle on -7 would be pi, so 7e to the pi I. This means we're going to do a substitution, ln of 7e to the pi I, and if you remember your natural log properties, this is the same as the natural log of 7 plus the natural log of e to the pi I, which is the same as the natural log of 7 plus pi I. And that is it. That is a number that is in a plus bi form. And if I had a grid and I put an ordered pair down to where this point is, it'd be the ordered pair, natural log of 7, comma, pi, over natural log of 7, up pi, and you have a place where on the complex plane, that is the natural log of -7. So I think that's neat that you can now do all this math that you couldn't do before. And here's another one. This one's going to take a little bit of time, but I would be remiss if I didn't show you this. The sine of something is equal to 2. Hopefully when you see that, you know that you can't take the sine of any angle and have it equal to 2 because sine is the ratio of y to r, and it's impossible for y to be bigger than r. However, you can do this in complex numbers. Here's how we start it. I'm going to start with just e to the theta I, just for a general theta. I'm doing this to kind of derive a formula for sine in terms of e's. I know that e to the theta I is 1 e to the theta I, and that's equal to 1 times the cosine of theta plus I times the sine of theta. Well, if I make this actually be e to the negative theta I, that would be the cosine of negative theta plus I times the sine of negative theta, which is equal to, cosine's an even function, so that's cosine of theta. Sine is an odd function, so minus I sine of theta. And if I take, so this is e to the negative theta I, I'm going to move this out of the way. And I'll just delete it because it's on a video. You can see it existed. And we're going to move this up. And I'm going to subtract minus, minus, plus. And I get e to the theta I minus e to the negative theta I is equal to 2I sine of theta, which means that the sine of theta is equal to e to the I, or theta I minus e to the negative theta I over 2I. So there's no way I would expect you to know this, but this actually gives me a formula for the sine of theta. So basically now my task is I want to figure out the sine of what is equal to 2. I'm going to set this equal to 2 and actually solve this for theta. So I'm going to do that first by multiplying both sides by 2I, so I get e to the theta I minus e to the negative theta I is equal to 4I. And then I'm going to multiply both sides by e to the theta I, so I get e to the 2 theta I minus 1 is equal to 4I e to the theta I. Let's put this in descending order, e to the 2 theta I, and I'm going to write that as e to the theta I squared minus 4I e to the theta I minus 1 is equal to 0. This is a quadratic. So let's use the quadratic formula. E to the theta I equals opposite of negative 4I, so 4I plus or minus the square root of 4I squared is negative 16 minus 4 times A times C all over 2A, and you get e to the theta I is equal to 4I plus or minus root negative 12. And root negative 12 is equal to, let's see, this is 4I plus or minus, the square root of negative 12 is 2 root 3I over 2. So I get e to the theta I is equal to, I can divide by the 2, and I can factor the I out. So I get 2 plus or minus root 3 times I. Now, that means theta I, if I take the natural log, is equal to the natural log of 2 plus or minus root 3 I, which by the properties of natural logs we can actually split up. So I'd get the natural log of, natural log of 2 plus or minus root 3 plus the natural log of I. So we're almost there. I know that I can replace I right here on the right. I is equal to e to the pi over 2I, because again, I is up on the axis. It's right here, so that's its complex form. So I have theta I, natural log of 2 plus or minus root 3 plus ln of e to the pi over 2I, which means that theta I is equal to the natural log of 2 plus or minus root 3 plus pi over 2I. And now we divide both sides by the remaining I. So I have theta is equal to the natural log of 2 plus or minus root 3 over I plus pi over 2. And dividing by I, well, if I multiply by I over I get, in final a plus bi form, pi over 2 plus, this would be actually minus, because the I times I is negative 1, minus the natural log of 2 plus or minus root 3 I. And these are two possible angles given the plus or minus in complex form whose sine value is equal to 2. Okay, your homework is this worksheet that you're going to find on OneNote and on the web, and actually I gave it to you a while ago, so you should have it. Come in with questions, feel free to post them and answer each other's questions on the GroupMe, and good luck.